All right, in this second of energy tutorials, we're going to take the concept of work to energy and bring it all together into the grand idea of the law of conservation of energy. So like the previous lesson, we're going to keep it short and sweet and focus most of our time, hopefully on practice, to put it together. It's critical, if you're going to do this correctly and consistently, that you simply keep track of energies. I'm going to use a little pie chart to get us thinking about it, but more than anything, like momentum, you just got to keep track of before and after, and things should fall into place. So pay special attention to that. All right, so let's bring it all together. We established earlier that work on a system changes the amount of energy in that system. Okay, so the basic idea is work goes to some change in energy. We learned that there's many types of that. It can be potential, kinetic, or even thermal, or a combination of all three. So if no more work is done, okay, we leave the system alone, then whatever total energy system the system has must remain the same. Okay? In other words, it's conserved. You can't create or destroy energy, you just simply change it from one form to another. Okay? So we can convert from one type to another. So we can go from potential energy to kinetic, kinetic to potential, potential to kinetic and some thermal, etc., etc. So the most succinct way of putting that algebraically is that the total energy that a system has because of work that was done on it at some point equals the total energy that it has at some other point. And the beauty is, when we look at conservation of energy, we could care less what happens between the 2 points that we're interested in. They don't come into play. Now, this statement can be expanded into basically the different types of energy. So we can talk about the gravitational potential energy. I was about to write PE, but I realized we're doing U's. So we can say U sub G plus whatever elastic energy we may have. Now, we haven't talked about it formally, but we might as well add it into that. Plus whatever kinetic energy we start with. So that's our total energy, potentially. Some of that could be zero, or we could have all three forms at once. That's going to equal whatever gravitational we have later on, plus whatever kinetic we have later on, okay, plus some elastic later on, plus some potential thermal energy that might be created. So it looks like a lot to keep track of, but in many problems you're going to have one of them at the beginning and another at the end, and then you just shift back and forth. So let's look at a simple schematic or example schematically. Okay, so let's say we have a ball that's rolling down a hill, and we have two situations. There is no friction and there's friction. So let's call this situation A, and this arrow will be situation B. Okay, so the work done on a system had to get the ball up the hill at some point, and it had to get it moving. But once we take work away, we want to look at what energy state it is in. So at the beginning, so that's our first pie chart. Let's say it's at a fairly high hill, so we've got a lot of potential. Whoops, I got to stop doing PE. Sorry. We've got a lot of gravitational potential. And how do we know it's gravitational? Because we're above and we're going to be falling down. And since it's moving, we're going to have, let's say, some kinetic. So now we go down the hill and there's no friction. So what's going to happen? Well, let's say we go lower portion. So we're going to have a shift. Let's say in our pie, we still have two pieces. There's no spring involved, and since there's no friction, there's going to be no heat generated. So we're going to have, most likely, since we're downhill, we're going to have more kinetic than we had before, and we're going to have less potential than we had before. So you can see that in terms of the share of the pie. So as something goes from higher to lower, it gives up some or all of its potential, and usually it goes to kinetic. It could also go to thermal, but we didn't have that case here. So in situation B, where we go downhill and there is some friction, then at the end we're going to have three types of energy, right? We're going to have less potential. We're going to have created some thermal. Now we're not sure which of these pieces is thermal. Let's say it's the smaller of the pieces. And what does that leave behind? Well, we went downhill, so we expect to have gained some kinetic, okay? And so when we go to do the algebra, it's just basically taking the values of each of these before and after and setting them equal to each other. Okay? And again, it doesn't matter, especially going uphill or downhill, how you got there or what got you there or how much time it took. All that matters is how high or low you started or ended. Okay, so let's do an example. we have a cat of a certain mass is launched horizontally with a certain speed from a height, and it's going to fall. Okay? And so if we look at this, this may seem like a projectile motion problem, and it is. And if we're ultimately interested in how fast it's going at the bottom right there, we don't have to do projectile motion anymore. We could, but now we have a much simpler way of doing it. So really pay attention to this and appreciate how easy it is. So in order to solve this, we're going to look in terms of energy transformations. In order to do that, we're going to look at what energy forms we have at the beginning, and then what energy forms we have any time thereafter, or any position thereafter. So we're going to break it up into 3 positions. Okay, so our first situation, let's look at our initial condition. So we have U sub G. All right, that's just nothing more than mgh. All right, so our M is 10, our G is we're going to call 10, and our H is 6. So we have 600 joules of potential to begin with. Kinetic energy, do we have any? Well, to answer that, we ask, are we moving? And we are. So to calculate kinetic, that's 1/2 mv squared. So 1/2 of 10 is 5. 4 squared is 16. 5 times 16 is 80 joules. All right, so we have a small amount of kinetic, and there is no springs involved here, so we're not going to look at elastic potential, and you don't start off with thermal energy. So our total energy at the beginning is 680 joules. All right, so now let's look what happens as the cat starts falling. So we can maybe put up here 680 joules. Well, we don't have to do that. All right, so we're going to look at 3 different heights. Height of 4, height of 2, and just before we hit the ground. Let's do the ideal first. Ideal means no thermal losses, and then we'll treat the thermal using the information. So how would we calculate our potential energy, gravitational, UG, at various heights? Again, it's mgh. So mg is going to be 100 times a height of 4, so we have 400 joules of potential when we're at a height of 4. We're going to have 200 joules of potential when we're at a height of 2, and of course we're going to have 0 potential just before we hit the ground. Now, where did all that potential go? The law of conservation of energy says our total energy at the beginning has to equal our total at the end. So if we started with 680 as our beginning, and when we're at a height of 4, we only have 400 potential, then our kinetic must be the total minus the whatever is in potential. So we are left with 280 joules of kinetic. And that's ideal, such that these two add to our total that we started with. So if we're right here at this point, let's say that's 4 meters above, we have a PE of 480. I'm not going to fit that on here. And a KE of 280, okay, such that our total is still 680. As we fall, we're going to have less potential. That's going to be more kinetic. So 680 minus 200, we have 480 joules. And then when we're at the bottom, there's no more potential, so it must all be kinetic, 680. And here's what's really neat about this. This might seem very simplistic, so let me kind of try to redraw this projectile part, okay. Here is our table, is that if we were doing this with kinematics and laws of motion, we'd have to take into account the vector nature of it. So we'd have to look at the vertical velocity and then couple it with the horizontal velocity and do vector addition to come up with the overall velocity. When you look in terms of kinetic or potential, since they're scalar, we don't need to mess with any of that. The energy equations take care of all that. So that's something to really try to appreciate. The reason we'd be interested in kinetic is to figure out how fast it's going. But I'm not going to calculate speed now because this is ideal and we have some real situations where there is friction. There is energy loss due to friction, and I believe I'm going to call this Q. Okay. So how are we going to calculate Q? Well, if you remember back from the previous lesson, we said that the thermal energy generated is equal to the work done by friction, which is the force of friction times whatever distance over which it acts. So let's calculate it here. Now, go back to our information. It says for each meter it falls, it feels 10 newtons of drag. Okay, so when we're at a height of 4, it has fallen 2 meters, right, from the 6, times 10 newtons, that's 20 joules lost to heat. After we're at a height of 2, we've fallen 4 meters, so 4 times 10 gives us 40 joules lost to thermal. And then when we're at the ground just before, we've fallen 6 meters, 6 times 10, there's 60 joules lost. Now we can calculate what the real KE is. So I'm going to put it at the bottom how we set it up. So basically what we're saying is our total energy that we started with is going to equal our total energy at any given point, which is going to be the sum of our new potential plus our new kinetic plus whatever energy, thermal energy is generated. So now we can look at the chart. When we're at a height of 4, we already know that our new potential is 400. Our KE we're looking for, and we had 20 joules. And that equals the top sum of 680. So we do the simple math, and we find that we're 20 joules short of our ideal. So we're going to have 260 joules of kinetic. When we're at a height of 2, we're going to be 40 joules short of our ideal. So that's going to be 440. And when we're falling a full 6, we're going to be 60 joules short of our ideal. So we're going to have 620 joules. So if you take, let's choose a column, take the bottom. If I take the potential plus the thermal plus the kinetic, they add up to the original total of 680. Okay, now why do I care about that? Because now I can find the speed. The speed we can use, KE equals 1/2 mv squared. So I'll leave it to you to work this out, but the velocity here should be around 7 point, and I can't remember the decimal meters per second. This should be 9 point something, and I believe this should be 11 point something. But again, it's important for you to work that out. And we've solved this problem using drag to figure out the speed without having to mess with any vectors. And that's a great thing. And by the way, if we had fired it up like this at the same speed of 4, none of the answers would change. Okay, that's really, really nice. So let's finish up with 2 more examples. What if the cat had slid down a frictionless chute? How would the values in the chart change for a given height? So instead of being projected forward, and let's say went down a slide of something like that, still the same change in height of 6 meters, no friction. Well, the total change in potential energy would still be the same, right? We'd still lose 600, no, excuse me, how much did we have? We had 600 joules of potential. The gain in kinetic energy at the bottom would be the same as the ideal. We would gain 600 joules of kinetic. Because there's no friction, there's going to be no loss to the thermal. And the beauty is we don't care how it got down. We don't care about the curvature. It doesn't matter. What matters is the change in height, delta H. Okay, so if we have that, then the final kinetic energy is going to be equal to what we gained plus what we started with, which would be 680. So that doesn't change. All right, next one. Got a few minutes left here. We're going to get this under 15 minutes. How does potential energy and kinetic energy vary with height? So we're going to do 2 different graphs, and this is something we should be able to work out. All right, so if our height is 0, we know we have 0 potential energy. When our height was 6, we know that our potential energy was 600. So how do we connect those 2 dots? Well, to verify what the shape is, we know that, we know that UG equals mgh, so we know that UG is proportional to h. So that means we connect it with a straight line. Okay, so that's our U sub g. Kinetic energy, well, when we were at 0 height, our kinetic energy was a total of 680, because we had 80 to begin with, plus we gained 600. And when it was initially at height of 6, it was at 80. So the question is, how do we connect those 2 dots? Well, KE is proportional to potential energy, and that's proportional to H, so that tells us we're going to connect these with a straight line, and we have that. And the really neat thing about these 2 graphs, we see as potential goes up, kinetic goes down, is if we look at the total energy at any given point, we see that the red represents sigma energy. If I take any 2 points, 1, 2, and add them up, I will get this red line. Okay, last one. Down to 30 seconds. You guys might have to do this on your own. So an arrow is fired with a velocity angle theta on the ground at a height h below where it is fired. In the place, if the place where the arrow hits the ground is given to be 0, write expressions for the arrow's total energy when it's shot from the bow just before it hits the ground. Okay, so I want you to work that out. List the types of energy and then how you calculate them, and then use conservation energy to solve it algebraically. And we'll talk about that in class. Okay, so if you have any questions, take notes, or take notes if you come in with some questions, and we'll do some practice in class.